Okay, picking up where we left off last time, we were doing a review, or new, for those who hadn't taken Chem before, of Lewis structures and how to draw Lewis structures. And so we left off with some examples of drawing Lewis structures. For drawing out or writing Lewis structures for a compound, you need to identify what's the compound, and we need to count up the number of valence electrons we have. So we're going to take each of the elements that we have and separate them out, figure out based on where they are in the periodic table what group or column they're in, figure out how many valence electrons each of them has, and we'll count those up. For CO, carbon has 4 valence electrons, oxygen has 6. We've got 1 of each, so we don't need to multiply these. We add them together, we get 10 total valence electrons. We also need our skeletal structure, so we started off with just the C and the O. We added 1 line to get them connected, and that uses up 2 electrons, since every line is 2 electrons. That left us with 8 remaining electrons that we placed evenly on the carbon and the oxygen, and then we sequentially moved in electrons to form a double bond first and then a triple bond to fill out our octets for our carbon and our oxygen. So they each have a triple bond, which is 6 electrons, and a lone pair, which is 2 electrons, giving them a full octet. We did the same idea for H2CO, and we can also do this for polyatomic ions. For polyatomic ions, the steps are basically the same, except that we've got a charge. And when we have charge, we add 1 electron for each negative charge, since electrons are negatively charged. We remove or subtract 1 electron for each positive charge. That's 1 electron for our total number of electrons. And then we also write the Lewis structure within brackets with the charge in the upper right-hand corner, kind of like we did with chloride, nitride. I think those were the 2 that we used. Anytime that we have a monoatomic anion, we also do this. So put it in brackets and charge in the top right corner. This would be for just chloride. For our polyatomic ions, they're bigger. We'll see an example of that right now. So we want to write the Lewis structure for ClO-, hypochlorite ion. We have 2 things. When you have 2 things, it's hard to get it wrong. Just don't put them right on top of each other, and it's a perfectly acceptable skeletal structure. We have chlorine, we have oxygen. Chlorine has 7 electrons in its valence shell. Oxygen has 6 electrons in its valence shell. And we have a negative charge. That negative charge means that we're adding 1 additional electron. So instead of 13 electrons, we end up with 14 valence electrons. In order for this to be a molecule or an ion, it needs to be connected. So we need to make sure that we have at least 1 bond in there. So we'll start off with 1 bond. 1 bond, 1 line equals 2 electrons, so 2 bonding electrons are used. That leaves us with 12 remaining electrons. And we are going to evenly place these 12 remaining electrons on the oxygen and on the chlorine. They currently each have 2 electrons counting towards their octet, which means that they each have room for 6. We've got 2 of them, 2 times 6. We can use up all 12 of our electrons by giving them as lone pairs. So we put 6 electrons on the oxygen, we put 6 electrons on the chlorine, and now we've got 0 remaining electrons to place. So all of our electrons have been placed. We've got the 2 in the bond plus 2, 4, 6 in lone pairs. Oxygen has its octet. Chlorine also has its octet. There's one thing that we're missing. The charge and the brackets. So we add our brackets and we add our one negative charge, and now this is a complete Lewis structure. We will also sometimes, somewhat frequently even, run into molecules that have more than one valid Lewis structure, such as with ozone. With ozone, O3, we put our oxygens in a row. We've got oxygen, so we've got 3 times 6 electrons. We've got 18 valence electrons. We place our 2 bonds to get everything connected. That's 4 bonding electrons. That leaves us with 14 remaining electrons. We've got 3 oxygens we can put, starting from the outside, 1 and 3, we can start adding electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that gets our oxygens 1 and 3 up to their full octets. So we placed 12 electrons. We have 2 electrons left. Those 2 electrons can go on oxygen 2. And that'll leave us with no electrons left. If we look at our octets, the ones on the outside are full because we gave them all those lone pairs. Our oxygen on the inside, our O2, our oxygen number 2, has 1 lone pair, which is 2 electrons. It also has 2 bonds, which are 2 electrons each. So oxygen in the middle only has 6 electrons. To get that 6 up to 8, what do we need to do? Double bond. So do we double bond? We can bring it from the left, or we can bring it from the right. Which one do we choose? Left or right? The answer is yes. Both. So we do the inclusive OR, and we end up with 2 different structures. So we're exploring all possible realities. Just erase everything. So we've got our double bond on the left, and our double bond on the right. And then we draw an arrow between them. To show that these are resonance structures. So this double-headed arrow says we're moving between the left version and the right version. The reality is some mixture of the left one and the right one. So when there are multiple equally good Lewis structures, draw all of them. And use double-headed arrows between them. This isn't like strictly, you'll do this every single time, all the time, but generally this is what we would do for when resonance structures show up. Although in reality, a lot of chemists will just know that there's other resonance structures, so you won't have to actually draw them. but in terms of this class, we will get to draw resonance structures. So the actual structure is called a resonance hybrid, and a resonance hybrid, just like a hybrid of two cats, if you mix two different breeds of cats together, you get out some third new version of a cat that's some hybrid of the two species. And for our chemicals, our two structures for ozone combined together, and it's something that sort of looks like each of them but is not either of them. So in reality, it's 1.5 bonds, or a strength equivalent to 1.5 bonds between the oxygens. In our Lewis model, the electrons are localized, meaning that we're setting them in one place. In nature, the electrons are often delocalized, so they're sort of spread evenly, 3 electrons across each of the oxygens, and they get to move back and forth. And that delocalization is resonance stabilization, and that lowers the energy. Resonance stabilization also results in, or is related to, a lot of compounds that are light absorbing. So like the phenolphthalein that we use in our acid-base lab as our indicator, that has something like this in it when it's in its pink form. All right, we want a Lewis structure for the NO2 minus ion nitrite, include resonance structures. So we've got NO2. In order for this to be symmetrical, we need the nitrogen in the middle. And so our skeletal structure is going to be, oh no. And then for counting up the number of valence electrons that we have, we've got a nitrogen. Nitrogen has 5 valence electrons. We've got 2 oxygens, each with 6 valence electrons. And what else? We've got an extra electron because we've got a negative charge. So the negative charge means we add 1 electron. So we'll have 18 valence electrons. To get everything connected, we'll put in some bonds. 1 bond between each oxygen and the nitrogen. 2 bonds, 2 electrons each. 2 times 2 is 4. So that's 4 bonding electrons. We've got 14 remaining electrons. We can distribute those electrons, and we want to start from the outside, so the oxygens, and work our way inside to the nitrogen. We can place 6 electrons on each oxygen. So we put 6 electrons on the left oxygen and 6 electrons on the right oxygen. We've got 2 electrons left because our oxygens both have their full octets. 3 lone pairs, 6 electrons plus another 2, that's 8. They've got their octets. And so we need to put the last 2 electrons on the nitrogen. So we've got no electrons left. Might be feeling a little bit of deja vu. Maybe. It's a similar trope. And so now we've got the choice. Well, nitrogen's not happy because it's got 2, 4, 6 electrons. It needs 2 more, so we need to introduce a double bond from the left or from the right. And of course, when there's a fork in the road, you take it. Just pick it up and say, thank you, universe. I was looking for another fork. So option from the left, option from the right, and we choose both. So option from the left, We've got a double bond on the left, option from the right. We've got a double bond on the right. And what else do we need? Brackets in the charge. And what else do we need? We need a cool little arrow in between them, showing that we're going back and forth. What else do we need? That one's a trick question. We don't need anything else. That's the full and complete resonance structures for NO2 minus. Questions about resonance structures? So resonance structures are a little bit weird. Let's do a check. Which of these is not a resonance structure of the ion shown here, the thiocyanate ion? One of these things is not like the other. Which one is different? Corporate needs you to spot the difference between these four structures. Which one's different? It's not A. A is a resonance structure. So resonance structures we're moving electrons. Or shuffling electrons. Number of electrons stays the same. Just where they are changes. We're basically just doing the little ball into the cup scam trick, moving the electrons around. So we could get from this to A if we move this left, any of these lone pairs from the left one in to form a double bond. We kick one of the bonds from our triple bond out as a lone pair. And we could get from A to C if we do that again. That'll get us from A to C. How would we get to B? What's changed? Yeah, we would have to move the nitrogen and the carbon, so those cannot be resonance structures. We've actually changed the chemical. I think those have different names. Circle that one because it is the different one. So the order of the atoms changed, not a resonance structure. So we're just shuffling electrons. We're not changing where any of our atoms are. I think I've told us about Lewis structures is sort of like a weird game that like your friend who's really into board games knows how to play, but you don't really know how to play it. And if we were in Chem 20, that's as far as we would go with, basically as far as we would go with this fun board game. But because we're in Chem 1, we get the DLC. So the DLC is formal charges. It's a game within a game. So once we've made a Lewis structure, there's another game that we can play with our Lewis structures. And formal charge helps us figure out the best Lewis structure. So this helps us find the best Lewis structure. This is also a simplification, so it's not always going to work, but generally it will work, and this is new to Chem 1. So the formal charge of an atom in a Lewis structure is the charge it would have if all bonding electrons were shared equally between the bonded atoms. So if you cut all of the bonds in half of the electrons go to the one on the right, half go to the one on the left, what would the charges on those atoms be? So chop all the bonds in half. Find the charge on the atoms. So this is a made-up charge that's assigned to each atom. We ignore electronegativity, so we're assuming that bonds are all shared equally. And the formal charge, our fake charge, is the number of valence electrons. So let's say that we've got a carbon, no, let's do nitrogen. And nitrogen is in a situation like this, where it's got a lone electron. How many valence electrons does nitrogen normally have? 5, because it's in group 5A. So it normally has 5 valence electrons, and we're going to subtract from that the number of non-bonding electrons that it has. In this case, just 1, the single electron, plus 1/2 of all of the bonding electrons. So the bonding electrons, we've got a double bond and a single bond, 3 lines, 3 times 2 is 6. We cut that in half, we get 3. Yeah. And so we end up with, oh, this isn't, whatever. It would end up with a 1 plus. The reason it ends up with a 1 plus is because I forgot about the octet rule coming up with the example. So it ends up with a 1 plus. So in this case, nitrogen would get a positive charge. You can also do this instead of using this equation, just chop all the bonds in half. So that would turn into dots on the left, dots on the right, stand up, sit down, fight, fight, fight. And now nitrogen owns those electrons. That's what I mean by chop them in half. Take each of the points, the ends of the lines, make those an electron. If it's on the side that's got that atom on it, you count it towards that atom. So if this is a Lewis structure for nitrogen, it should have 5 dots. It has 4 dots. It's 1 short, so it's a 1 positive charge. Again, it's a fun game to play, obviously. /S. The sum of all formal charges in a neutral molecule must be 0. The sum of all formal charges in a neutral molecule must be 0. The sum, adding up all the formal charges in an ion, must equal the charge of the ion. So NO2 minus, for example, should have an overall -1 formal charge. Small or 0 formal charges are better. So our goal when we're doing formal charge is minimize the formal charges, make them as small as possible. Small negative charges, small positive charges. Ideally, we get zeros for everything. If formal charges cannot be avoided, negative formal charges should be on the more electronegative or most electronegative atom. This is only if we need to have formal charges that are negative. If we don't have to have negative formal charges, then ideally we just get zeros for everything. All right, we can use formal charges to discriminate between 2 or more equally good Lewis structures, things that we would otherwise not be able to know what's the best configuration, what's the best orientation, like for HCN. So for HCN, we can come up with a structure with carbon in the middle. We can come up with a structure with nitrogen in the middle. That's the real dilemma that we're working with. So we've got HCN, nitrogen and carbon have a triple bond, or HNC and carbon with the lone pair. Our structure A, our structure B. And if we check our formal charges, one of the ways that we can do that is cut all of our bonds in half. I'm drawing in dots as blue dots to represent the ends of the bonds, and we'll count those towards the atom that they're next to. So in structure A, hydrogen has 1. Then we've got our carbon in the middle with 4 dots. We've got our nitrogen on the end, 3 dots from the double bond or triple bond, and 2 from the lone pair. Or the other option, where we've got nitrogen in the middle and carbon on the end. I like thinking of it in terms of cutting the bonds in half and counting those as the number of valence electrons rather than using the subtraction thing that's shown in the slides, but it's a matter of personal preference. So if we're looking at structure A on the left, hydrogen normally has 1 valence electron. It has 1 valence electron. So hydrogen is going to get a 0 for its formal charge. And that's also true in structure B. In structure A, carbon normally has 4, and it has 4, so it has the amount that it wants. So that also gives it a 0. Nitrogen normally has 5, and it has 5, so that gives it a 0. There's going to be no net charge on the carbon or the nitrogen. They've got the number of valence electrons we expect them to have. However, if we look at structure B, nitrogen normally has 5, and here it has 4, so it's 1 short. That would give it a positive charge. So it's got a +1. It's got one fewer electron than it normally has. Carbon normally has 4 valence electrons, and here it has 5. It's got 1 extra electron. Electrons are negatively charged, so it gets a 1 minus. So it's a minus 1. So if we're choosing between these two, we're going to go with structure A because it's zeros across the board for formal charges, and smaller formal charges are better. Questions about how much fun we're having with our Lewis structure DLC? All right, assign formal charges to each atom in the 3 resonance forms of N2O, where nitrogen is one of the nitrogens is essential. Which resonance structure is likely to be the most correct structure of N2O? How many electrons does nitrogen like to have? How many does it have as valence electrons? 5. What about oxygen? 6. So 5 valence electrons, 6 valence electrons, because they're in group 5A and 6A, or 15 and 16. So let's look at A. We can do the cut the bonds in half method. Our nitrogen on the left has how many dots around it when we cut the bond in half? It has 6. And it normally has 5. It likes to have 5 when it's by itself. It has 6. That's 1 extra. So that's a minus 1 for its formal charge. The nitrogen in the middle, again, likes to have 5, but it has 4. So it's 1 short. It's minus 1, but it's a negative charge, so it's a plus 1. We love electrons and them being negative and making life so confusing. Oxygen has 6 dots around it. It likes to have 6, so that's going to give it a 0 charge for its formal charge. Go ahead and do the formal charges for B and C. All right, coming back to resonance structures and our formal charges. For B, let's look at our nitrogen on the left. Nitrogen likes to have 5 electrons. We're going to subtract from that the total of the lone electrons, which is 2. Plus half of the electrons from bonds, which is 6. So the 1/2 times 6 makes 3. So 2 plus 3, that's 5. So 5 minus 5, that formal charge is 0. So we've got a 0 formal charge on our left nitrogen. Our nitrogen in the middle is going to have plus 1. Our oxygen on the right is going to have minus 1. Because it's got 7 electrons basically that it has ownership of if you cut the bonds in half. And then version C, our nitrogen on the left has 7 on it, and it likes to have 5. That's going to be a minus 2. Nitrogen in the middle is going to be a plus 1. Oxygen on the right is going to be also a plus 1. Some checks to make sure that we did the formal charges correctly. N2O is a neutral molecule. So formal charges should add to 0. So in structure A, -1 + 1, 0, that's a total of 0. B, 0 + 1 - 1, that adds to 0. C, -2 + 1 + 1, that also adds to 0. So we're good there. You could also, I guess if you really trust that you did the first two right, a -2 + 1, you could just guess that the last one's a +1 because it has to be for it to be correct in terms of formal charges. Which one of these is definitely not the best? C. Why C? It doesn't have any zeros. All the numbers are bigger. C is the worst, because the numbers are bigger. So we are now choosing between A and B. Both A and B have a +1 in the center. So we're choosing, who do we give the -1 to? Do we give it to nitrogen or oxygen? How do we decide? The more electronegative atom gets the negative formal charge. So we have to figure out which one is more electronegative, nitrogen or oxygen. So if we're picking between A and B, which is more electronegative, nitrogen or oxygen? Where does our electronegativity emperor reside? There they are, fluorine. Fluorine gets the value of 4, that's the highest number. Things that are closer to fluorine also have higher numbers. So oxygen is closest to fluorine, nitrogen's a little further away. That means oxygen's going to have a higher electronegativity value. And so oxygen will get the negative charge, which means that B is the best structure. We can also draw Lewis structures for organic compounds like diazomethane. And we are going to have some resonance structures. And we are going to need to pick the best one based on the formal charges. So diazomethane is CH2N2. And you might think that there's 4 things bonded to the carbon. If you build it that way, you will never get your full octets. So what actually happens is that carbon is in the middle, the nitrogens are stacked, essentially. So this is going to be the structure that we build out. We get some bonds to connect everything together. We can do more bonds, and we're going to need some lone pairs on the far nitrogen. This is not how I would expect you to come up with it. I just want to skip past the Lewis structures part. So this is one possible configuration. We could also have this, where we've moved one of these lone pairs from our nitrogen in to form a triple bond that kicks some electrons out of this left bond onto the carbon as a lone pair. Now carbon's got a lone pair, nitrogen's got a lone pair. We need to figure out which of these is better. And so we can use formal charges. Our hydrogens have one bond. As long as hydrogen has one bond, it's happy, so we can ignore hydrogen for formal charges. I'll just write in the zeros so we don't have to worry about those. In our structure on the left, our carbon likes to, when it's by itself, have how many valence electrons? 4. Likes to have 4. If we look at how many ends of bonds are touching the carbon, 1, 2, 3, 4. Carbon has 4. It likes to have 4, so it gets a formal charge of 0. Nitrogen in the middle likes to have how many valence electrons? 5. And how many ends of bonds are touching it? 4. So it's got 4 electrons that it owns in this situation. It wants to have 5. It has 4. It's 1 short. It would be a 1 positive charge because of the fun that we get to have with subtracting a -1. And then the nitrogen on the right also likes to have 5. It's got 2 4 electrons that are just on it. Plus, it's got the 2 tips of the double bond. So 4 plus 2, it's got 6. That's 1 more than it likes to have, so it gets a -1. Questions on how we got those numbers? Okay, structure B, structure on the right. Our carbon likes to have 4. We'll do the adding them up version this time. It's got 2 electrons that are just on the carbon as lone pairs, and there's 6 bonding electrons. It gets half of those. So 1/2 of 6, which is 3. 3 plus 2 is 5. 4 minus 5. The carbon's got a -1. Nitrogen in the middle is actually in the same situation as the nitrogen on the left. We just moved one of the bonds to the right side. So this one's still a +1. And then the nitrogen on the right has 2 electrons from the lone pair, and it's got the 3 ends of the triple bond. 3 plus 2, it's got 5, it wants 5, it gets a 0 formal charge. So now we have to pick between structure on the left, structure on the right. And the difference is in one, the carbon's 0 and the nitrogen's -1. In the other one, carbon's the -1 and nitrogen's the 0. So the question we should be asking ourselves is carbon or nitrogen more electronegative? Which one's closer to fluorine? Nitrogen's closer to fluorine. Nitrogen is more electronegative because it's closer to fluorine. So it is better to give nitrogen the -1 football club formal charge. So we are going to choose the version on the left for our Lewis structure. That's the one that's probably going to be around most of the time. The one on the right can occur. It just probably won't be around quite as much as the one on the left. Questions before we move on from formal charges? You can use, again, you can use the subtraction addition method. That works all the time. If you get the hang of counting the ends of the bonds plus the dots that are on it, I think that's faster and easier. They're doing the same thing though, so you should get the same numbers either way. We also have exceptions to the octet rule, one of those being odd electron species. So free radicals have odd number of electrons. That means they end up with a single electron. So somewhere in the Lewis structure there will be one electron by itself. Normally that would mean to us something's wrong, because we should have lone pairs or bonds, and those are both even numbers of electrons. We can have odd numbers of electrons. That will end up with a single electron somewhere in our Lewis structure. These tend to be unstable and reactive. If we look at the Lewis structure for NO, nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. We do some bonding electrons. We've got some remaining electrons. We're going to dish out six to oxygen, 3 to nitrogen, perhaps. And that should use up all of our electrons. 2, 4, 5. Nitrogen only has 5 electrons. We need to move one of these in to form a double bond. So there's a double bond. Oxygen now has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 7. And we can't get an even number. So we just have to do which version is best based on formal charges, because we could also equally have the lone electron on oxygen. Formal charges would help us decide which of these is correct. If we do formal charges for the top one, we get formal charges of 0. For the bottom one, we get formal charges of -1, +1. Move some electrons around again. So formal charges inform us the top structure is better because it's got zeros for its formal charges. Again, this is free radicals, just having a lone electron by itself. Anytime that you have an odd number of electrons, you should end up with a free radical species. Which of these molecules would you expect to be a free radical? What do we need to have a free radical? A single electron, which means that we've got an odd or even number of electrons. Odd number of electrons. So we see free radical, lone, single electron. That means we've got an odd number of total valence electrons. So if we count up the number of valence electrons, that should show us which of these 4 structures is going to have an odd number of electrons. If we look at CO, Carbon has 4, oxygen has 6. That's going to have 10 total valence electrons. If we look at B, that's going to have 16 valence electrons. That's also an even number. If we look at N2O, nitrogen has 5, but we have 2 of them. So that's going to be 10 plus another 6 from oxygen, also 16. And D, chlorine has 7, oxygen has 6. So we've got 13 valence electrons. It's got to be D. D is going to end up with a free radical. We can also have incomplete octets. So some elements tend to form incomplete octets. They don't get to 8. Boron forms compounds that have 6 electrons. Boron is happy with 6 electrons instead of the typical 8. So it gets a hextet instead of an octet. If we do a Lewis structure for BF3, it'll look like this. We would not do a double bond because it would screw up our formal charges. As written, this is zeros across the board. If we double bond it one time, our fluorines that are single bonded have zeros, but we'd have a -1 on our boron and a +1 on our double bonded fluorine. So that could be one excuse why we only get triple bonds, or 3 bonds. We get zeros for the formal charges, and that's just better. Aluminum also sometimes does 6 electrons. But since it's a metal, we don't do a lot of formal charge. We don't do a lot of Lewis structures with aluminum, where it'll end up with octet stuff. But it'll also be happy with 6 electrons, like an aluminum trihydride, AlH3. Beryllium also tends to have incomplete octets. Boron is the big example. Boron is okay with 6 electrons. That's the whole takeaway from the incomplete octets, essentially. Boron is okay with 6 valence electrons. It's a weird one. We can also have expanded octets. And expanded octets can happen in elements in period 3 and higher. So things that are below period 3 on the periodic table can also do this. They can often exhibit expanded octets of up to 12 or 14 electrons, only for things that are in period 3 though. So if we do ASF5 or SF6, we can get fun stuff like this. Honestly, the most annoying part of these, if you know what the structure is already, is just drawing in all the dots. So arsenic in the middle has 5 bonds, 2 electrons each. It's got 10 electrons on it. But this is a good Lewis structure. SF6, similar idea, but now we've got 6 fluorines and all of their dots. Like that. Sulfur has 12 valence electrons on it. If we did formal charges, sulfur has a formal charge of 0, arsenic has a formal charge of 0. So these would be perfectly okay having these expanded octets. These are both stable compounds, and the reason for this is that the d orbitals can take the extra electrons. So starting in period 3, we get d orbitals. D orbitals become available in n equals 3, which starts in row 3 of our periodic table, and everything below that also has d orbitals. And we don't fill them up until we're one row past. So they're a little bit higher in energy, but they're empty. So these sort of act as extra pockets that sulfur, arsenic, and other large compounds, things that are lower on the periodic table, they're extra pockets that those things can put electrons into if they need to. Let's look at formal charges on sulfuric acid with and without an expanded octet. Sulfur in the middle with 4 oxygens on it. 2 of those oxygens have hydrogens on them. And then we get to do all the extra lone pairs. I'm fairly confident that this is correct without doing any calculations. So this is without expanded octet. Our oxygens that are bonded to hydrogens are okay. They've got 4 electrons from lone pairs, 2 more from the bonds, because they've got the ends of the bonds. They like to have 6, they have 6. Those oxygens are just fine. Hydrogen's got its 1 bond, it's also fine. If we look at our oxygens that are by themselves, they've got 2, 4, 6, plus 1 more from the end of this bond. They've got 7 electrons. If we do 7 taken away from 6, that leaves us with a -1 formal charge. We'll also get the same thing for our oxygen on the bottom. And then our sulfur in the middle does have a full octet, but if we look at the ends of the bonds that are closest to it, it's touching 4 electrons. It likes to have 6, so it's too short, not the wrapper. So that's going to be a +2. +2, 2 -1s, not ideal, but maybe not the craziest thing. However, with octets, expanded octets, computer, expand octets, we get instead two double bonds. Now if we look at our octets, or our formal charges, our oxygen on top has 2 4 electrons in terms of lone pairs. It's also got the ends of the double bond. So it has 6 electrons around it that it can call its own. It likes having 6. 6 minus 6. Formal charge is 0. The bottom oxygen also gets a 0 for its formal charge. And if we look at the sulfur in the middle, because it's got 2 double bonds now, it's got 6 electrons around it. So the sulfur has a 0 for its formal charge. So now everything's got 0 formal charges. Everyone's actually happier than they were before. Happier in quotation marks. And that's our formal charges explanation for why we expand the octet, because it reduces formal charges. So our takeaways: we can expand octets to lower formal charges for period 3+ elements. If they're in row 3 or below, we can expand octets. Period 2 elements never have expanded octets. If they're in the second row, they don't have d orbitals, and so we can't expand their octets. They don't have accessible d orbitals. So another useful way of using formal charges. Let's write the Lewis structure for XeF4, and actually I'm going to skip this because I want to try to finish the lecture, because I think we're close enough that we can still finish it today. So moving on from that, bond energies. We can also use bond energies to estimate enthalpy changes for a reaction. Bond energy is the energy to break 1 mole of the bond in the gas phase. This is always going to be positive because energy is required to break bonds. A bond is stronger if it takes more energy to break. So bigger number equals stronger bond. Compounds with stronger bonds tend to be more stable and less reactive. They're harder to break the bonds. And if you can't break the bonds to rip up your molecule, then it's hard for you to rearrange it and put it into some other form. For bond energy, we are going to use average bond energy. So thanks to physical chemists that have calculated bond energy for a lot of different compounds, we can have an average bond energy. So this is the average of the bond energies for that particular bond compared across a large number of compounds. So for example, the energy required to break a CH bond varies slightly depending on the molecule. If it's in H3C and the last thing that the carbon's bonded to is a hydrogen, it's 438 kilojoules per mole. If there's 3 fluorines instead of the 3 hydrogens, it's 446 kilojoules. If they're bromines or if they're chlorines, they're also slightly different molecules. So this is why we're using an average for this CH bond. So we use an average value of 414 kilojoules. This lets us do an estimate. It's roughly about 414 kilojoules just across any given compound. So we're always going to be off by a little bit since we're using averages. Double and triple bonds have higher bond energies than single bonds because they're stronger bonds. When we're doing bond energy stuff, we get to use a bond energy table like this one from our book. So the bond energy in kilojoules per mole, and then whatever the bond is, hydrogen bonded to hydrogen, hydrogen to carbon, and so on and so forth. And we've also got some double bonds, triple bonds, all that sort of good stuff. So you might have to hunt through here a little bit when we're working on bond energy questions. You don't ever have to memorize bond energy numbers. You'll always be given them if you need them. The way that we estimate enthalpy changes for a reaction is using the average bond energies. We're going to take the sum of all the delta H's for the bonds that are broken plus the sum of the delta H's for all the bonds that are formed, and this is going to be a negative number. So breaking bonds takes energy input. Energy required to break bonds. So when bonds are formed, energy is released. Energy released when bonds form. This also, does this work out to products minus reactants? I don't think it does. No, it's backwards. All right, so add up the enthalpies for all the bonds that are broken, and then add up all the bonds that are formed. That number is going to be negative. We're sort of subtracting bonds broken minus bonds formed, depending on how you think about it. We'll show an example. If we want to estimate the enthalpy change for bonds formed, example from the book, if we've got methane and chlorine, the first thing we need to do is break the bonds. We need to break all of the carbon-hydrogen bonds. We've got 4 of them. So 4 CH bonds break, 1 Cl-Cl bond breaks. So we'd find the values for these, 4 times whatever the CH bond is, plus the Cl-Cl bond. That's the amount of energy it takes to break the bonds. And then we would look at what the products are. Our products are CH3Cl. I guess we're just breaking 1 CH bond. Page to look ahead. And we're also forming HCl. So forming CCl, HCl. So it would be CH plus ClCl plus negative CCl plus negative HCl. Overall should be a negative number. We've previously, I think, said that energy is stored in chemical bonds. Breaking a bond requires energy, so the opposite is also true. Forming a bond releases energy. I think it's easier to remember that breaking bonds requires energy and then flip it. You have to put energy in to break bonds, so you have to release energy to form bonds. I think that's the easier way to come up with energy releasing when you form bonds. We're going to skip that to get to our calculation. A potential future fuel, maybe in the past, I don't know if this is still current, is methanol. Write a balanced equation for the combustion of gaseous methanol. Use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So we're starting with methanol, CH3OH. It's a combustion reaction. It's going to react with what? Oxygen, which exists as as a gas. What's its chemical formula? It is O2. And that's going to go on to form CO2 and H2O. Balancing things out, our carbons, we've got 1 on each side. For our hydrogens, we've got 4 on the left side, 3 plus 1. On the right side, we've got 2. Got to get those numbers up. So we put a 2 in front of our H2O. Now our hydrogens are balanced. Last thing to balance is oxygen because we've got O2 by itself, so we can change that one for free. If we look at the right side, we've got 2 plus 2 for 4 oxygens. On the left side, we've got 1 in methanol and 2 in O2, so we've got 3. So we need to add 1 more oxygen, but we can't change our methanol or we screw up our carbons and our hydrogens. So we need a 3/2 in front of our O2. And now this is the 2's cancel, 3 oxygens plus 1 more to give us 4. And we can't have that 3.5 be there because this isn't a standard enthalpy of formation, standard heat of formation. So we can't have coefficients that aren't whole numbers, so we just multiply everything by 2. So that turns into 2, 3, 2, and 4. Just to very quickly go through the balancing. And I'm going to delete some of that so we have room. Now we need to know what bonds do we have, which means we need Lewis structures. So we get to do Lewis structures for all 4 of the molecules. They will look like this. So these can be somewhat involved problems, as you might have been able to guess. I'm drawing 2 because we've got 2. And then for our O2, oxygen has a double bond with another oxygen. We've got 3 of those. That's going to form 2 CO2s. Carbon double bonded to 2 oxygens and 4 H2Os. And I'm going to shrink our table. Oxygen with 2 lone pairs and hydrogens, and we've got 4 of those. So we've got the correct coefficient number of molecules on the left side, on the right side. We need to now count up all the bonds. So on the left side, we've got CH bonds. We've got 6 CH bonds. 3 in each methanol. We also have CO bonds, 2 CO bonds, and we've also got 2 OH bonds, and that's just our methanols. Then we've got 3 oxygen-oxygen double bonds. We're using the red here. On the product side, we've got C double bonded to O bonds. How many of those do we have? Carbon double bonded to oxygen. How many of those bonds do we have? I don't think it's a trick question. I just want to make sure that we're counting them correctly. C double bonded to O? 4. Yep, just 4. And we also have oxygen bonded to hydrogen. We've got 4 waters. We've got 2 of those bonded each. 2, 3, 4, 5, 6, 7, 8. We've got 8 OH bonds. Shrink the waters to give us a little room. So we need to take our bond energy table. We need to find our CHs, our COs, our OHs, our O to O with double bond, our C to O with double bond, our O to H. We're reusing the OH. So our CH is the same as HC. So 6 times 414 kilojoules per mole. I'm going to be, oh, I grabbed the wrong thing. Too much. I'm going to be a little lazy here and move that units all the way to the end to save us some space. We also need 2 COs. We find our CO, it's still in the first column, it's 360. Two times 360. We also have 2 OHs. It's the same as HO. So plus 2 times 464. And our 3 oxygen-oxygen double bonds. Which is in the middle column, 498. So that's our sum for breaking. And I don't have my calculator out. The total is 5,626 kilojoules per mole. And again, that's the energy to break. And then we have to look at the energy to form the bonds. So we're looking for C double bonded to oxygen. Carbon double bonded to oxygen has a value of 736. That little star, though, says that it's 799 in CO2. We have CO2, so we're going to use that number. So forming bonds. When we form bonds, do we put energy in or do we get energy out? We release energy, so we're using the negative. So it's 4 times negative 799, and we're reusing the OH bond up here, which is 464. We've got 8 of them. So 8 times negative 464. And this will also have units of kilojoules per mole. 4 times minus 799 plus 8 times negative 464. We get negative 6908 kilojoules per mole. So 5626 minus 6908 kilojoules per mole gives us negative 1,282 kilojoules per mole. For this reaction, that would be our delta H on the side. Questions? I have typically, I think in the past I've put one of these questions as a short answer. Less involved than this, but still it's one of these, so it's going to be long regardless. But expect one on exam 4. Last couple of slides. Average bond length. Average bond length is just the average length of the bonds for a large number of compounds, like we did with bond energies. Double bonds are shorter than single bonds. Triple bonds are shorter than double bonds. Generally, long bonds are weaker. There are some exceptions to this. Here's a table of bond lengths, the different bonds, how long they are on average in picometers. In metals, metals have low ionization energies. And so in a metallic solid, all of the nuclei just sort of float next to each other and their electrons are floating around them. We call it an electron sea. And this explains conductivity. So the reason that metals can conduct electricity is because their electrons can move freely, so they can wash through this metal sea. It also explains their malleability and ductility. Since they're sort of just loosely held by the general charge around them, that means they can also like rotate around each other. They're not held by these really strong directional bonds like in molecules. So you can move them around. Oxygen has a double bond. Ozone has weaker bonds that are an intermediate between single and double bonds. So UV light from outer space, from the sun, from other stars, when it hits ozone molecules in our upper atmosphere, that energy gets absorbed into those intermediate strength bonds, and it can break the bonds in ozone. Bonds in O3 breaking absorbs harmful UV light, which means that it doesn't get to us. So in the past, there's been this scare of, oh no, the ozone layer is being depleted. Perhaps you've heard of the ozone layer depletion. There's a hole that would form kind of annually around Antarctica where the ozone layer is getting really thin because of chlorofluorocarbons and other ozone depleting chemicals. And so when the conditions were just right, the ozone layer would basically get torn apart. There's no more ozone layer. So lots of dangerous UV light was making its way into Antarctica. Fortunately for us, most of us don't live in Antarctica, so it wasn't a problem. The globe also, people all over the world recognized that this was a serious problem and made regulations to cut down on ozone depleting chemicals. And so now we don't actually have this scare anymore, which is probably why you haven't heard about it in a long time, because we banned the chemicals that cause the ozone layer depletion. And so the ozone layer has basically gone back to normal. If it had continued, though, it's possible that those effects would have worked their way further around the globe, and we could have seen people in the low southern hemisphere starting to get higher rates of skin cancer or getting really extreme sunburns during the time of year that this polar vortex activity stuff was happening and causing the ozone layer to deplete. Questions?
What were those chemicals used for?
I think a lot of the chemicals were refrigerants, but I'm not 100% sure off the top of my head. Not exclusively refrigerants, and some of them are still used. It's just that we've cut down the amount that they're allowed to be used, and there's like special permitting and stuff for most of those.